Assalamu alaikum viewers. Here we are with another interesting topic in this series of programs on physics. A topic very close to our lives. Computers, television, tape recorders, compass, telephone, transformers and many more. All equipments work making use of magnets. Let us discuss details in steps. In the lab, some of your colleague students are doing experiments. Let us join them. Busy?
Yes.
What is the business?
Experiments with magnet.
Wonderful. Would you tell us, please?
Of course. Well, magnet has particular properties. First, it always points in north and south directions when we suspend it freely. These ends are north and south poles. Second property of a magnet is that like or similar poles, like both of them are south poles, they repel each other. You can see the repulsion here.
We are nowhere.
On the other hand, unlike or opposite poles, like this is a south pole and this is a north pole, they attract each other. Another magical quality, you cannot break a magnet. All broken pieces of one magnet possesses all the magnetic qualities. In other words, we cannot separate north and south poles.
Very good. Can you add something, please?
Of course. Well, I'll try to create and observe the magnetic fields. We bring this bar magnet under the paper. You see, these iron filings, they arrange themselves in a very regular pattern. They are making the curved lines, and the intensity is maximum at north and south poles. It gradually reduces as we move away from the pole. The magnetic lines, they never intersect or overlap each other.
Are you playing a game only?
No ma'am, I am observing magnetic lines of force, and I have observed firstly magnetic lines of force cannot pass through air, which I show you. As there is air, there is very little movement in the pen. Secondly, I have observed magnetic lines of force easily and strongly pass through the iron pens, which I show you. Magnetic lines of force pass through the paper pens, which proves this property.
Physics is the branch of science which relates matter and energy and the interaction between them. Now we are with the teacher. Madam, what are you going to prove?
Yes, I am going to show you that Oersted was the first man who proved that magnetic field is created around a straight wire carrying current. This is a long straight wire connected to the battery. The positive terminal is connected here. As you can see, current flows through the circuit. As the direction of flow of current is in the upper direction, we notice then when magnetic compass needle is brought near the wire, long straight wire, deflection is obtained in it. This deflection is noticed to be anti-clockwise. Ampere was the first who proved the presence of magnetic field around the long straight wire with the help of his right hand. According to the right hand, if the direction of flow of current is in the upper direction, we hold the wire in our right hand such that the thumb points in the upper direction. We curl our fingers round the wire to show the presence of magnetic field around it, which is anti-clockwise. This can also be proved with the help of iron fillings. If I sprinkle iron fillings around it, they cluster round it in concentric circles, showing a regular pattern. These concentric circles are obtained around the wire. If we reverse the terminals of the battery, the direction of flow of current will be downward. According to the right hand rule, if we hold the wire in our right hand such that the thumb points in the downward direction, our fingers they curl round the wire to show the direction of magnetic field, which is clockwise here.
Is it applicable in curved wires too?
Yes, if we take a straight wire and we curve it in the form of a helix, a new thing is formed which is called solenoid. Solenoid can be circularly taken as toroid. It can be made like this. If we make holes in a paper and we pass a wire through these holes, for once the direction of flow of current is away from us. For secondly, direction of flow of current is towards us. Circular loops or turns are obtained. The direction of flow of current is directed outward, for once it is inward, obeying the right hand rule. This is also applicable when we prepare it like this. This is a solenoid I have prepared. The current is passing through this solenoid. This is a long wire with many turns. The current is moving circularly in these turns. This is the south end and this is considered to be the north end. When we bring a piece of iron or a bar, iron bar, inside the solenoid, it gets magnetized. If we hold this wire in our right hand, the thumb points in the direction of magnetic field and our fingers they curl round to show the direction of current in the wire, which is anti-clockwise. The solenoid behaves in the same manner as the bar magnet. The field inside the solenoid is uniform and it is directed from south to north, just as in the bar magnet. It is circular and curved outside the solenoid. It is linear inside and curved outside. Similar is the case with the circular coil. Uniform field is created in the center and circular field around the circular wire.
So, up till now we have studied the properties of magnetic lines of force and their applications in long wires, solenoids and toroids. Now we see what is the Fleming's left hand rule and what are its applications. Would you please add something?
Yes, Fleming's left hand rule is applicable when we stretch our fingers. The first finger points the direction of magnetic field. The middle finger points the direction of flow of current. Our thumb points the direction of force, magnetic force. This is a galvanometer in which a horseshoe magnet is attached. It is a moving coil galvanometer. When current passes through the coil rotates. The spring which is attached with the iron core, it makes the needle move. Fleming's left hand rule is applicable in galvanometers.
Can it be changed into other forms too?
Yes, there are other forms also, like ammeter and voltmeter. An ammeter is made by shunting a galvanometer, that is, attaching a resistance wire in parallel to a galvanometer. When a resistance wire is attached in parallel to a galvanometer, a new thing is formed which is called ammeter. Ammeter notes current. A voltmeter is such a device which is made when a resistance wire is connected in series to a galvanometer. When current passes through it, potential difference is noted through a voltmeter.
Dear students, it is important for you to understand the fundamental principle and system of electromagnetism. Electromagnet function as a basic unit in a number of equipments. Let us try to get the details.
Assalamu alaikum and welcome, dear students. In this portion we are going to study electromagnetism and its application on your daily life. By now you have been studying the charges at rest and the force that they exert on one another, called as electrostatic force. Let us now consider the moving charges. In this case, an important force comes into play called electromagnetic force. This force produces magnetic properties in different materials. Let us now consider when a charge is exposed into a magnetic field. When a charged particle Q enters a magnetic field, it is forced to go on either one side of the field. This provides an evidence of the existence of some force experienced by the particle. The magnitude of this force is given by the equation F is equal to QVB sine of theta. Let's find out how magnetic force varies when we vary the angle between the field and the velocity b. When the angle is 0 between the direction of motion of the velocity and the magnetic field, then the force experienced, the magnetic force experienced by the particle, is minimum or 0. Reason being the angle is 0. Now let's see what happens if we change the angle to 90 degrees. We see that it will experience maximum magnetic force. Now remember, the direction of this magnetic force is always perpendicular to the velocity v of the charged particles and the direction of magnetic field. Let's see what happens if the moving charged particle remains in a uniform magnetic field. When a positive charge enters with a velocity v in a magnetic field directed into the paper, then a perpendicular force will push it upwards. If it stays within the field, then it follows a circular path. Remember, for a negative charge, the direction of the force experienced will be reversed. But remember, this magnetic force only changes the path of the charged particle. Let's investigate how and what are the other factors which do affect the path of this charged particle. In this experiment, we have two big coils called Helmholtz coils producing a uniform magnetic field. The electrons from electrically heated cathode emerge as a narrow beam. The coils produce magnetic field at 90 degrees to the beam. When the field is switched on, the beam, the green color beam, follows a circular path. If we now increase the magnetic field, that will increase the magnetic force, and hence it reduces the radius of the circle. Now if we increase the voltage supply between the cathode and anode, that will increase the speed of the charged particle, and thus the radius of the circle. The diameter of the circular path can be measured by a scale behind the tube. Having known the diameter, we can always find the radius of the circle. Charge to mass ratio can thus be calculated using the equation E over m is equal to 2v over b square times r square. Having known the radius and charge to mass ratio enables us to find velocity of the charged particles. In addition to velocity of the charged particles, we can also find the nature of these charged particles. So far we have been discussing the magnetic effects on a moving charge. Think what will happen if these charges start to move through a conductor. We all know this will give rise to an electric current. So the force experienced by the conductor should be the summation of all the charges moving through that conductor. The apparatus arrangement that we have is what we have to do: supply from one of the terminals of the battery, one going from negative to the conductor. This is a copper wire acting as a conductor. The other terminal of the battery will go into the second piece of wire, we have mercury providing a conducting path. This is mercury in a container providing a conducting path for the conductor, and we are going to observe what happens when the current flows through the conductor, if it experiences any magnetic force or not. This is a magnetic field present. Let's see the effect of this magnetic field on the conductor. When I turn the voltage supply on and I increase the voltage supply, means increasing the current, see the wire is experiencing a repulsive force. If I increase the current, the force increases even more, and the wire is going further away from this piece of wire. Now let's see what will happen if I increase the magnetic field. Means I can attach one more magnet to it. Now we have an increased magnetic field, keeping the length of the conductor same. If I again supply the current through the conductor, let's see what happens now. Now see, the force experienced by this conductor is even greater. It is going for the same given voltage, it is going even further. Now let's see what will happen if I change the length of the conductor, keeping the same magnetic field. Now when we change the length of the conductor, we shall see what are the effects, whether do we have the same force experienced by the conductor or not. I have a different length, a bigger length, and force is experienced as soon as I turn it on. For a smaller voltage, we shall see that we have a larger deflection. A larger deflection is there for a smaller voltage. Now let's see what will happen if I reverse the direction of current. All I have to do is switch over the terminals. So now I have positive end of the battery going to this end of the conductor and the negative to this small piece of conductor. Let's see what will happen when we switch it on. Now see, there is a force of attraction rather than repulsion. Now the wire is moving towards the other piece of wire, which proves that when we reverse the direction of current, the direction of force also reverses. Let's take a look at different applications of electromagnetic induction. One application of electromagnetic induction is a transformer, something that we have usage all over our houses and buildings. Let's see the construction of transformer. It comprises of two coils wrapped around an iron core, a soft iron core. The coil which is being connected to the input power supply is called as a primary coil. The other coil is called as secondary coil. We can connect some output to this. Depending upon the number of turns of primary and secondary, we can change the output. Now if I increase the number of coils for primary and I decrease the number of coils for the secondary coil, then the output that we will gain will be lower than the input. Similarly, if I increase the number of turns of wire for the secondary coil and decrease for the primary, then the output for the secondary coil will be more as compared to the primary. Now depending upon the ratio of primary and secondary coil, a transformer is either called as step down transformer or a step up transformer. Step down transformer is the one in which the number of turns for the primary coil is more than the number of turns for the secondary coil. Now let's see if I supply 220 volts to the primary coil. Now if I give 220 volts for the primary coil, let's see what do we get as an output. We have 5 different terminals. Each terminal represents different number of turns, giving different output. The output, let's see what we get. If I connect these 2 terminals, what we do get is close to 3 volts. So the output that we get is approximately equal to 3 coils. If I attach the probe to the other terminal, means I'm increasing the number of turns as I go from this terminal to this terminal. See the change in output for the voltage output for the secondary coil. If I now have increased the number of turns, see the voltage output goes till about 10 volts or 8.5 volts. If I further increase, it goes till like 50 volts. So such a transformer is called as a step down transformer. The reverse case will be a step up transformer. By now we have discussed many applications of electromagnetism. For instance, DC motors, generators, transformers, high-speed trains, levitation of trains, and many more. This is not just the end of it. You can explore even further. And I believe that this program would have been helpful for you.
Magnet have particular properties. First, it always points in north and south directions when we suspend it freely. These ends are north and south poles. Second property of a magnet is that like or similar poles, like both of them are south poles, they repel each other. You can see the repulsion here. On the other hand, unlike or opposite poles, like this is a south pole and this is a north pole, they attract each other.
You see, these iron filings, they arrange themselves in a very regular pattern. They are making the curved lines, and the intensity is maximum at north and south poles. It gradually reduces as we move away from the pole. The magnetic lines, they never intercept or overlap each other.
According to the right hand, if the direction of flow of current is in the upper direction, we hold the wire in our right hand such that the thumb points in the upper direction. We curl our fingers round the wire to show the presence of magnetic field around it, which is anti-clockwise. Yes, Fleming's left-hand rule is applicable when we stretch our fingers. The first finger points the direction of magnetic field. The middle finger points the direction of flow of current. Our thumb points the direction of force, magnetic force. This is a galvanometer in which a horseshoe magnet is attached. It is a moving coil galvanometer. When current passes through the coil rotates. The spring which is attached with the iron core, it makes the needle move. Fleming's left-hand rule is applicable in galvanometers.
If we now increase the magnetic field, that will increase the magnetic force, and hence it reduces the radius of the circle. Now if we increase the voltage supply between the cathode and anode, that will increase the speed of the charged particle, and thus the radius of the circle. The diameter of the circular path can be measured by a scale behind the tube. One application of electromagnetic induction is a transformer, something that we have usage all over our houses and buildings. Let's see the construction of transformer. It comprises of two coils wrapped around an iron core, a soft iron core. The coil which is being connected to the input power supply is called as a primary coil. The other coil is called as secondary coil. We can connect some output to this.